Now that we've gone over how to write an expression for both Q and K and use Le Chatelier's principle to predict which way a reaction will shift, we can now use something called an ice table to mathematically calculate how much of a reactant or a product we will have at equilibrium. So if we are met with the reaction A goes to B, and there's an equilibrium reaction, let's call them both aqueous. Now, what we can do is we can draw an ice table. Now, the letters in this ice table, I stands for initial. This will be the initial concentration of both A and B. So let's call B, we can call B 4 molar and A 2 molar. So this is what we start at. The change will be what happens during the reaction. Are we going to go to the right and make more B, or are we going to go to the left and make more A? So we don't know that yet because we have not wrote our Q expression and we do not know what K is yet. Then E is going to tell us the equilibrium concentrations of both A and B. So the first thing that we need to do is write our expression for Q. So Q is products over reactants. So this is B over A, which will be 4 molar over 2 molar, which will be 2. Now, let's call K. I'm just going to make up a K value for this reaction. Let's call K 3. So K will be equal to 3 over 1. So this will be our K value, meaning that at equilibrium, we should see 3 times as much B as A. So let's go through and solve this ice table. So the first thing that we need to do is we need to decide whether Q is equal, less than, or greater to K. So as we can see, Q is 2 and K is 3. So Q is less than K. So what we can do is we can say, we know that this reaction needs to proceed to the products. So we want to push this reaction in this direction. Therefore, we can increase Q and it will catch up to K and we can eventually get it. So Q equals K and we are at equilibrium. And remember, every reaction is chasing this equilibrium where Q equals K. So what we can do, we know that we are going to the right. So we can say this is minus X. This will be plus X. This shows that we are going to lose A. And where is the A going? Well, it is going in the forward direction to make B. That's why we can add B. Now, we need to be really careful to remember our coefficients. If these coefficients were 2, this would be minus 2x. And if this was 2, this would be plus 2x. Any coefficient you have to put in front of that x value, meaning every time you run this reaction, it would actually be minus double that, or because I started this reaction with just 1-to-1, which we'll keep it for this example, we can just call this minus x and plus x. We can think of it as a 1-to-1 ratio. So what does that mean for our equilibrium concentration of both A and B? This will be 2 minus x. This will be 4 plus x. So what we can do is we can plug that in and solve for what x is going to be. We know that K is equal to products over reactants. Well, our products here, the B concentration is going to be equal to 4 plus x, and our reactants concentration is going to be equal to 2 minus x. And what is this equal to? Well, we know from before that K is going to be equal to 3. So we can solve. We can say, we can do this algebra right here. We can say that multiply both sides. We can say that this is 6 minus 3x equals 4 plus x. We can say that 4x equals 2 and x equals 1/2. So we know x is equal to 1/2. So we can substitute that in. This is going to be minus 0.5. I turn it to a decimal, plus 0.5. This is going to be, so instead of 4 plus x, we know this is 4.5. Instead of 2 minus x, this is 1.5. So let's see if it checks out. 4.5, number k is equal to products of reactants. For 1.5, this is equal to 3. So this checks out. So ice tables are a great bookkeeping method to keep track of everything throughout the reaction. They're also really important to solve for this change that is going to happen in a reaction, as well as the equilibrium concentration of either a reactant or a product.